5, 6, 15, 6, something like that. So this is a short section, and then I'm really just tempted to give you a formula and move on. But let's talk about deriving some of this, because it is a little interesting. And the thing about the surface area is that there's more to these types of integrals than what we're going to see today. And we're going to come back to the idea of a surface integral that's based on a surface area that we're looking at now. So let's start with a surface that's defined by z is equal to f of xy. You knew that was coming, right? So z is equal to f of xy. And when we're looking for surface areas of these types for today's for this section, we're looking at a particular domain, and it doesn't have to be rectangular, but for our sake right now, let's just make it rectangular. And essentially what we're looking for is a surface area that's up here. And we're trying to find out what that surface area is, or trying to compute that surface area. So like we've been doing, what we've been doing with these double integrals, we're going to take our domain and we're going to partition it, and we're going to take a look at little things. So what I wanted to do in this partition is just take a look at one little subrectangle. And let's blow that up a little bit. There's your little subrectangle. And what I want to do is I want to try to match that up with what's happening up here. And so up there you'll have a surface Oh, I meant to draw that in black. Oh, I meant to do that in blue. All right, here's what I wanted to do this in black. And then my little magnifying glass in blue. All right, so this is what we have. And what happens here is that I can just take one of these corners. I don't know which corner. I suppose I should take this corner over here. It doesn't really matter. But if I take this corner, I have these vectors that are flat on the xy plane. I guess they don't have to be vectors for right now. Right now we can take a look at them as lengths of something. And they are delta y and delta x length. And if you remember back when we were starting to talk about this, that this area over here is, at this point, not important right now, but the area over here is the dA, or let's call it delta A. That's that area element that you multiply the function by to give its height so that you can find its volume. But we're not going to focus so much on dA as we are going to focus a little bit more on the dx dy. So for us to find the surface, what we're going to look at is take our dx and dy elements over here and put it up on the surface. And we're going to put it on the surface where it is going to become the derivative. And so this little size of delta y will go up as a vector And then this little vector delta x will go up as a vector. Let's see, I'm trying to make this so that I can draw something else after this. That would just have been projected up there. But now, from a two-dimensional vector to a three-dimensional vector, we now have a third component. We need to include that third component. And so the third component, if we pick this x naught, y naught over here as the tails of the vector that got shot up to here is now on the surface, and that surface point will be x naught, y naught, and then z naught, which is f of x naught, y naught. Okay, I don't really care about that. But what I do care about is what these vectors are. And so the vector will be kind of like, it would be a shadow image of the delta y vector, which does not move along the x, right? It doesn't move along the x. And it has a delta y unit along the y. And now I'm curious to figure out what is my z component of this thing. How is this changing with respect to z? So, do you understand what I'm looking for? Because I'm going to ask you. Okay. So, if I take a look at this vector that's lying on the floor, remember these are really the smaller squares over here, right? If I'm looking at these vectors that are lying on the floor, this vector is going in the y direction. So it does not move along the x direction. It's fixed at x. So this has a vector, I guess I should use my vector notation. This has a vector 0, delta y. That's a two-dimensional vector. Now if I bring this up to 3 dimensions, I want the same x and y components of my vector because it's right underneath. And now I need to figure out what my z component is. What? Well, I could call it delta z, but then we want to be able to describe it a little bit more. So it's some change in z. Yeah, so not quite delta z. So let's I don't want you to give me the answer yet. I want you to first understand the question. So my question is, do you understand the question? Maybe. Okay. Not quite the curvature, the tangent. So what I'm looking at is I basically want this vector to be tangent to the surface at that point, x naught, y naught, or up there, x naught, y naught, z naught.
When x is stagnant as well. So
and when x is fixed as well. So x is fixed, and I'm moving along in the y direction, and I'm moving along in the y direction with a step of delta y. And so I want to see how my z changes when my x is fixed and I'm moving along the y. What is that quantity? Partial with respect to y. Okay? So unfortunately, it's not just that, since now I shrunk this vector to have not unit length, but a delta y length. So I want to factor this by delta y as well. Okay? So now I just have to think, is it divided by delta y or is it multiplied by delta y? Because if it's rise over run, this is the rise, and this is the run. So if I put Fy over delta y, and I divide it by delta y, am I going to get the slope, which is Fy? No. Because I'll get Fy divided by delta y, this is the rise, over the run,
And then get double the.
and then I'll get Fy over delta y squared. So I don't want that. So I need to multiply, not divide. All right, so my rise then will be Fy delta y. Okay? So I've successfully transferred this little mini vector down here, which I enlarged over here, up to the surface as a tangent vector with the same y length and not moving along the x. And so it's up looking like that. So I want to do the same thing for the other side. Well, so I have delta x, and then not moving along the y, and then so fx delta x. So that's my vector. What are we looking for again? What's the big picture? We're looking for the surface area. So if I have a, what am I going to do with this? What happens when you take a cross product? What are you looking for? You make a normal vector with a, you do that? So it's a normal vector, but how is this related to the surface area?
The magnitude is the surface area.
So the magnitude of the normal vector happens to be the area of the parallelogram. So if we make a little parallelogram up there, it's not exactly the surface, right, because the surface is curved. But if I take this flat little mini plane and add up a whole bunch of them, then I will get a good approximation. And then, of course, you Riemann sum it and it becomes a double integral, and then that's the end of the story. Well, not quite the end of the story. Let's find the cross product and take its magnitude. So these are the two things that we're crossing. And since we are going to take its magnitude, it doesn't matter which one goes first, right? So I don't know. It doesn't matter which one goes first. So the area this one I want in purple now. Area of parallelogram. Can I just put parallelogram?
Save so much time.
So the area of that one little mini parallelogram is going to be the cross product, the magnitude of the cross product of these two vectors. I didn't name those vectors, so I'm just going to take the cross product and take the magnitude of it. I don't know. I, J, K. So the first one, I'll put 0, delta y, Fy, delta y. And then delta x, 0, Fx, delta x. So in the I, okay, so cross out the I, and then I get Fx, delta x, delta y minus 0. So Fx, delta x, delta y minus 0. And the middle term is negative 0 minus Fy, delta x, delta y. And then the last component in the K is 0, 0, and then negative delta x, delta y. And so I want the magnitude of this. So I have to square each one, put it on, all under a square root. So Fx delta, I'll put fx squared delta x delta y squared plus fy squared delta x delta y quantity squared plus negative, and so I'll just call it a positive delta x delta y squared. Pat? Yes, I'm dying to do that. I should have done that earlier. So you take out a delta x delta y squared that's under square root, so it just becomes a regular delta x delta y, and then all you have left is a square root of fx squared plus fy squared plus 1 delta x delta y, which in a Riemann sum will become dx dy. So that's just for that one piece of parallelogram, and you do that over a region in your double integral, then you would have covered the whole region below, and then you would have had little mini parallelograms all over the place. Okay? So the bottom line is this will end up being your formula, and so your surface area, let's go to a fresh new page here. Surface area of z is equal to f of xy over a region is going to be given by, let's call it SA, double integral over the region of your function, well, not over your function, but fx. Should I say fx? Is that okay, or the partial or curly? Okay, so fx evaluated, I guess I don't need that either. And so this is a dA. Yeah? Because we can. Well, I mean, you know, surface area in Calc 2, if you think about the surface area you guys have found a surface area because you had to do a volume of revolution. But if you just have a regular surface, well, first of all, you guys never really talked about regular surfaces back in Calc 2 because, yeah, well, they require functions of x and y, and you guys didn't talk about functions of x and y then. So the surface area that you guys might have done in Calc 2 would have been a surface area that's obtained by a volume of revolution. And if it's a volume of revolution, then all those surfaces have something in common. And the thing that they have in common is that they are all circular. Over here, we can now take a look at any surface and find the surface area of those. Okay? All right, so this is our formula, and this is how it's derived. And the book asked you to look at this and compare it to our, what's it called? Arc length formula.
It's the same.
So compare it to arc length formula. Which is a single integral from a to b of so what? Yeah, so it's very similar. There's more. What? I'm trying to hold out on you because it's not covered until later on. It's one of those things where, is it going to be on the test? Well, not this one. Then I don't want to hear it. All right, so so this formula, let's do a couple examples, and then let's, we're going to go past this. Oh, here, just to get some visuals of this, I wrote something a while ago, I guess. The saddle is always a nice thing to look at. So we partition our domain, nice equal partitions, and then we take a look at some tangent vectors. And the tangent vectors that we're looking at are based on a particular sub-partition down below on the xy plane. And then so if we get that tangent vector and then we find the magnitude of the cross product of those tangent vectors, you essentially get this, you can't really see it, but that's supposed to be a parallelogram over there. So the idea is that you got one of those, and then you do a whole bunch of them, and here's what you have. So let's get rid of the surface. Wait, which one is the surface? Oh, this is the actual grid. So these are actual parallelograms. I took the surface out, and so as you can see, there's little cracks and openings between them. But this is the set of all the parallelograms that we're looking at. Suppose we can make bigger cuts instead of so if we take a look at bigger parallelograms or less partitions, this is how your sum would look like. And of course, with less partitions, you'll have a more rough estimate. And the more partitions you have, the better your estimates will be. The smoother it'll look. Okay. All right. So that's the general picture. Let's see if we can find some examples from the book or homework. How does your homework look like for this, actually? $15.6. No, you only have 4 problems. Watch a video. Is this a lab? No. It's an actual homework. Maybe I should change it.
There's something who've already done it. Yeah, I mean.
All right. Stop. Just stop. Sound like my kids. Just stop. Oh, man. I'm going to pick something from the book. You guys only have 4.
I looked at like a week back, it's like, let's do all of these. We only have 4.
All right, let's find the surface area part of the sphere. Notice the sphere is not an actual sphere also. It's kind of shifted, so that's going to be a little tricky. Part of sphere that lies inside of the paraboloid. Oh, man, I don't know how to do this one. All right, let's do this one. Look at that sphere over there. You see that plus 4z? If that was a constant, then that's the square root of that is your radius or something, and then that's all. It's all good, centered around 0. But now your z is over there. It's not centered around 0 anymore. So you may want to, well, I don't know, to complete the square to try to figure out what this thing actually looks like. So let's do that. Because this is your actual surface is the sphere, so you want the sphere as z is equal to something, and then you have another paraboloid. So before I try to draw this, I want to get a better view of what this might look like. So if I bring everything into the other side and try to do the completing the square business. That's going to be equal to 0, and then I can ask myself what I need to add to make this a perfect square. I think it's 4, right? Plus 4 on the other side as well. So that's going to give me my radius. And now I get to see x squared plus y squared plus z, and this is a minus, right? Minus 2 quantity squared is equal to 4, and if I just write 2 squared, then I know my radius is going to be 2. So my sphere is actually centered around 0, 0, 2. 0, 0, 2. So this is the center of my sphere, and it has radius 2, so I'm just going to be touching the xy plane. All right, so I'm drawing my sphere now, touching the xy plane. It should look something like this. And now my paraboloid goes from here, and it goes up, I'm assuming. The sphere that lies inside of the paraboloid. So I'm assuming that out here, the sphere is outside, and then somewhere along the way over here, it's going to intersect. So we're probably going to set them equally each other to find an intersection. But the actual part of the sphere that I'm interested in is in here. Okay? So now let's try to find an intersection. I have my paraboloid and I have my sphere. That's a little bit simplified. So I can set them equally each other, so to speak, and that just probably means put the z in, put the paraboloid in for the z in there. So let's find that intersection. We got x squared plus y squared plus z minus 2 quantity squared, and so the z is x squared plus y squared, and that's equal to 4. And let's see if we can work this out to get this into a nice circle. Is that the best place to put that, or maybe better if we put it up here in the original one? Yeah, I'd have to FOIL, but this is already kind of worked out. So let me see if this is a little bit easier. Let's combine it here. So we got x squared plus y squared plus z squared is equal to 4, and then z squared, or just 4z. I don't know if that was any easier, but let's see. It's a little bit easier.
Yeah.
So let me bring the x squared and y squared to the other side. So this will be 3x squared plus y squared. And then let's FOIL this out. X squared plus x to the 4th, right? 2x squared y squared plus y to the 4th is equal to that. I don't know.
Wait, why did you cross out that first x squared y squared?
Because I brought it over to the other side. Oh. So, I have another idea that might save us from all this stuff. Yeah. So I see a lot of x squared plus y squareds kind of laying around, and really all we're shooting for is the shadow on the xy plane. And so in an attempt to try to figure out what the shadow on the xy plane is with x's and y's, I kind of have a feeling that this is just going to be a circle. So it might actually be better if we take it from here. I don't think so, because the sphere went straight up, and the paraboloid is just going up. So let's take it from this equation here, which is x squared plus y squared plus z squared is equal to 4z. And wherever we see an x squared plus y squared, let's just replace it with an r squared. So let's make a note here that r squared is equal to x squared plus y squared, and we'll just go straight into polar coordinates. This is probably not a very good first example. We have r squared plus r squared squared is equal to 4r squared. So it looks like we just bring all the r's over to one side or something. So I have an r to the fourth minus 3r squared is equal to 0. And factor out an r squared. And so r is equal to 0. It's not going to be of any interest to us, although that is one place where they meet. And then r is equal to square root of 3 would be what we would be looking for. And we want, of course, the positive side, because the negative side just means that your r is on the other side. So it looks like our domain, or our region that we're integrating over, can be turned directly into polar coordinates, with r going from 0 to square root of 3 and theta going all the way around to 2 pi. Okay? All right, so now that we know that, we have our function. No, we don't have our function yet. We need to solve for z to get our function. And completing the square will help us solve for z. So z is equal to, we have a 4 minus x squared minus y squared. And then we need to take the square root of that. And then we need to add 2. So again, with spheres, there's a top and a bottom. So the top is the positive of that square root, and the bottom is the negative of that square root. So we're going to take the positive of that square root. So our function z is equal to, let's say, 2 plus the square root of 4 minus x squared minus y squared. What? We are, but we still need to take the derivative of this with respect to x and with respect to y. All right, so let me take this on to the next page. So now that we've made a big mess already. So this is what we have. We have our domain and we have our function. That's all we really need. Now we need to figure out all the rest of the stuff. So the rest of the stuff is we need your fx. So I get a 1/2 4 minus x squared minus y squared to the negative 1/2 times the derivative of the inside minus 2x with respect to x. And simplify that, the 2's will cancel. I have an x in the numerator, negative, and then a 4 minus x squared minus y squared with a square root in the denominator. And I'm thinking my y is going to be the same, right? So your y is essentially going to be the same, except the derivative of the inside will be 2y, so you'll have a y in the numerator. We need to square each one of these, and then eventually add them. So fx squared will give me a positive x squared over 4 minus x squared minus y squared. Fy squared will give me a positive y squared over 4 minus x squared minus y squared without the square roots. So I put that in the formula and add 1. So in the integrand will look like this. Fx squared is x squared over the denominator squared. No, it's already squared. And then fy squared is this. And then we add 1 to it. And so it might be worth doing common denominators and stuff, because I see x squared plus y squared, which in polar coordinates will become r squared, but then there's the numerator will probably also have an x squared and y squared. So let's make this one a 4 minus x squared minus y squared over the same thing. So our integrand will have an x squared plus y squared plus 4 minus x squared minus y squared. So I added the numerators together. The denominator is 4 minus x squared minus y squared. So yeah, so the x squares and the y squares in the numerator cancel. I just have a 4. So that would be a 2, and then I just have the square root in the denominator. Oh, that was rough. So the surface area is equal to, I don't want to set it up with r's yet. I'll just rewrite it first with the x's. I got this whole formula boils down to a 2 over the square root of 4 minus x squared minus y squared dA. Now let's do our substitution into polar coordinates, and I can put my correct limits now. I have a 2 over the square root of 4 minus r squared, and then the dA becomes r, dr d theta. And so the extra r there will be very useful in our, make this into a u substitution instead of a trig substitution. And we have r going from 0 to square root of 3 and theta going from 0 to 2 pi. teacher would like to be done. Is this okay, or should I punch it into Wolfram Alpha? We could do this by hand. Yeah. All right. Split it to two integrals, 0 to pi d theta. So that's going to be 2 pi times your integral from 0 square to 3 of a 2 root 4 minus r squared r dr. So u substitution should take care of this. U is equal to 4 minus r squared minus 2r. So everything is there except for the negative sign. So I'll keep the minus 2, the 2, and then throw out the negative sign. So we have 2 pi, and this integral now becomes an integral in u. I don't know if you guys switch limits or something like that. I don't like to, so I'll keep this as remind myself that this is an r limit. And the 2r dr changes to a du with a negative sign over square root of u, which is u to the 1/2, right? So negative sign out in front, and u to the negative 1/2 du. So I'll add 1, so u to the positive 1/2 times what? Oh, divided by 1/2, so times 2. And we're going to evaluate this for r going from 0 to square root of 3, 2 pi, negative 2, square root of 4 minus r squared from 0 to root 3. So put the square root of 3 in there. I get square root of 3 squared is 3, 4 minus 3 is 1, so negative 2. And then minus negative 2 times this 4, square root of 4, which is 2. Yeah, what's this equal to? plus 4 is 2, so it's 2. Pi. Whew. That was too much. All right, is that cool? All right. So it might have been nicer if we actually had an easier example with constant limits and a nice function given to us, but here we go. This is about as bad as it gets. What? So eventually we'll need to parameterize surfaces and do some more interesting things, but let's talk about let's talk about how to parameterize surfaces, and then for the kinds of surfaces that we're dealing with. I have the 3D plotter calculator that I was thinking about using instead of trying to do some other stuff. And you know how to parameterize a curve in 2 and 3 dimensions, right? We can parameterize a curve in 2 or 3 dimensions, and let's just draw this one. Let's get rid of the other one. So we can parameterize a curve by just letting x equal to some function of t, y equals some function of t, and z equals some function of t, and then it's going to draw out some sort of curve. But what we can do also is instead of having one parameter like t, where you would get a one-dimensional figure like a curve, we can have two parameters where we can have a two-dimensional figure. So let's think of a plane that's not one of the coordinate planes. Like z is equal to 4 minus x plus 2y, for example. Okay, so instead of drawing a space curve, what we can draw is what's called a parametric surface. So now this is a surface that is drawn out by two different parameters. And those two parameters can be known as s and t. In most graphing programs, they're called u and v. And we can also think of them as x and y. Okay? Oh, maybe I should have done this differently. Oh, well. So if you want to draw this surface, what you could do is you can let x equal to one of the parameters, and you let y equal to one of the parameters. And then you can let z equal to whatever z is equal to with the appropriate x and y parameter. So if z is equal to 4 minus 2x minus 2y, I can replace my x with what x was supposed to be equal to, which is u, and then I can replace what y is equal to, which is v, and then ask this thing to graph, and maybe it'll graph. Now, some parts of it should be there. 4 minus 4u times. That shouldn't make a difference. Oh, yeah, maybe. All right, let's put some negative numbers here. Negative. Oh, zoomed out too much. Oh, I think I have to press that. I don't know. That's a bummer. What's going on? The what? Oh, there's got a point there somewhere. It's not drawing the surface though. What's going on? U and V. Yeah, I suppose. Is it because it was too steep? Is that what happened? Well, So,
There's so many things rotating.
parametrizing surfaces. One way to parameterize a surface is to just let your x be one variable and your y be one variable, which it already is, which is kind of silly to think about and say out loud. But it is a form of a parametric surface. So parameterizing surfaces, if we have a z is equal to f of xy function, a relationship between x, y, and z in this way where you can get z as a function of x and y, then we can have a parameterized surface. And I don't know if I should write my vector vertically. I think it might be easier that way. But x is going to be some function of some variable. Y is going to be another function of another variable, and then z is going to be essentially the same function, except you're going to replace x with u, and you're going to replace y with v. And so you have this parameterization. Okay? So this is sometimes called, I don't know if the book calls it this, but I like to call this a graph parameterization. And then you know how we compare things with a lesser dimension? If you remember back in when we first started talking about parameterized curves, if we have y as a function of x, like those y functions that we've been studying and in 2 dimensions from pre-calculus, we sometimes did a parameterization where we have a parameter t, and then we just let the independent variable x equal to that parameter, and then your dependent variable would be the same functions, but instead of x, we're going to put t in. So it's the same kind of business that we did back then, where we're still going to let the independent variable be independent, except instead of calling it x, we're going to call it t. So that's the same thing over here. We're going to let the independent variables, there's 2 of them, still be independent, but instead of calling x and y, we'll call it u and v. Okay? So let's go back to the graphing calculator and imagine parameterizing something like a paraboloid. So we would parameterize a paraboloid by saying u for x, v for y, and then for z, what should it be? So the paraboloids, the basic paraboloids, x squared plus y squared, so you just have u squared plus v squared. And let's go from -1 to 1 here so we can see a nicer picture of the paraboloid. So this is a paraboloid. Now, I don't know if you guys ever wondered why this paraboloid looks like this, because when I draw a paraboloid on paper, I don't have these corners going up there, right? I guess one better if we just stick with one. So, did you guys ever wonder what the deal is with this spikes on the corners?
Yeah,
if you look at it from the top, you see essentially the domain of how this is being drawn out. So we can say that given our domain, and our domain is like x, or our domain is u and v, the u values go from -1 to 1, and the v values go from -1 to 1, and they just happen to be the x and y values, right? So we're essentially looking at the x and y values when we're graphing this in the graph parameterization. Now, what can you say about the equation of the parabola? Paraboloid. And how do you think we can change this so that we're using a different domain? So our paraboloid has a radial domain? What's a radial domain? Like a circle? What do you mean a circle? Instead of a square? Okay, let's think of what AJ's trying to say and take it a step further. Circle what? No. Polar coordinates. So imagine parameterizing this now. Instead of doing the graph parameterization like we just did, let's see if we can try to do it using a polar coordinate parameterization. If you look at x squared plus y squared, I mean, it's right here, right? I was going to say it's staring you in the face, but maybe it wasn't so obvious. But x squared plus y squared in polar coordinates, we know that to be r squared. So what if we change our parameterization style? Instead of going into the u-v business as the x and the y, let's change our parameterization so we're representing r and theta, which is in polar coordinates. So let's take the same example, this paraboloid example, and try to parameterize this using polar coordinates. Now, for polar coordinates, we know that we have restrictions on x's and y's, right? So in polar coordinates, let's go polar. In polar coordinates, we're kind of restricted to keeping the x and y as whatever x and y is supposed to be. What is x supposed to be? And y is r sine theta. But now when you see the pair x squared plus y squared, together, you can always replace that with an r squared. So if you let z equal to r squared, then you got yourself a polar coordinate parameterization. Now, the good news is that was easy, wasn't it? The not so good news is it's not really bad news. And the graphing programs restrict you to just using u's and v's. So you just have to remember that your u is r and then your v is theta. So if you approach it that way and call this u cosine theta, u sine theta, and then instead of u squared plus v squared, we just have, what's r again? R is u squared. Then, I don't want to draw it yet, because when we change this, we're going to have r and theta being described as how we want to parameterize this. So if we let our theta go from 0 to 2 pi like we always do, and we let your r go from what to what? 0 to 1 maybe, then we might get something. Oh, v. So I need to adjust my r, like you guys said, to go from 0 to 1, and my theta to go from 0 to 2 pi. Now I have that same paraboloid that doesn't have those spikes going up on the sides anymore, right? So it's just a paraboloid that's cut flat. And if I want it to go a little bit higher, I just let my u get bigger, and it's still cut flat up on top. Right? What? Why? Because if we look at the shadow on the xy plane, we see that that now is describing that circle that was our domain. And if I change, if I decide my theta to not go all the way up to 2 pi, but instead going to pi, then I only get half of that paraboloid. And if I actually have it to go 4 pi, you won't see it, but the paraboloid will draw itself out in 3 dimensions as a surface twice. But this is how we can approach our surface a little bit differently now through what we call a parameterization. So we have a parameterized surface. So let's see. Now this is going to play an important part when we actually study the surface integrals, because part of what we're going to need to do is we need to be able to look at a surface and parameterize it in several ways. So this is a polar parameterization. We talked about the graph parameterization a couple of slides ago. And then we're going to go to other types of parameterizations that deal with a particular coordinate system, not just polar coordinates, but with some other coordinates. Okay? So a couple more playing around things. If we change the u squared to just a u, what do you think is going to happen? So it would be the square root of x squared plus y squared, which is a cone. What if I made this into a constant like 0? What do you think is going to happen? It's a plane, but still we're going in a circle, right? So it's a disk. And if I change this into a 1, then it's a disk that's moved up 1. Okay? So doing these parameterizations, surface parameterizations, will be important for us later on. Is that going to be in a test? No. All right. Hopefully the surface integrals won't be too bad. If you get stuck with an integral, put it into Wolfram alpha, and then get your values that way.